So let's start with the third lecture by Professor Moraga about higher dimensional Fano varieties.
Thanks a lot, Michela, for the introduction. So today I will talk about singular Fano varieties. So on Monday we discussed smooth Fano varieties and what we know about them. And essentially I tried to explain that a full classification of higher dimensional smooth Fano varieties seems not attainable. But at least we can prove a lot of, or at least I gave a couple of samples of some theorems that we can prove. And the picture for log terminal singularities that we discussed on Tuesday was pretty similar. We can sort of classify some cases in low dimensions. But then in higher dimensions, everything that we can do is mostly a qualitative study rather than quantitative. There are some few cases in which we can do more quantitative results. So today I will talk about singular Fano varieties. So let me start with the very naive question. Why singular Fano varieties? Right, so this is a very fair question because if we're already struggling to try to understand smooth Fano varieties, why do we try to do something harder? Well, let me give you a couple of answers. So first, the study of singular Fano varieties allows us to understand symmetries. Understand symmetries of a smooth Fano varieties. Right, so if you have a finite group acting on a smooth Fano variety, then it's very likely that the quotient will be a singular Fano variety. So, you know, these appear naturally when you want to study symmetry, finite groups acting on smooth Fano varieties. So some second reason, and this is the more, let's say, the more honest one, is that singular Fano varieties naturally appear, singular Fano varieties naturally appear when compactifying moduli spaces of smooth Fano varieties. I should mention here that there are some moduli spaces of a smooth Fano threefold that has been constructed using K-stability theory, but like moduli spaces for smooth Fano varieties in general is still work in progress by many people. But in any case, even in the examples that we have, even when you want to compactify, let's say, a family, an affine family of smooth Fanos, it is very likely that you will get some singular Fanos in the limit. And the third reason is that actually it helps to study Calabi-Yau manifolds. It is also likely that when you degenerate a smooth Calabi-Yau manifold, in the central fiber, you will not get just one singular Fano variety, but they often break into many Fano varieties. So smooth Calabi-Yau manifolds, often admits degenerations to reducible varieties where the central fiber has singular Fanos as irreducible components. So you can think about the classic picture of an elliptic curve degenerating in three rational curves. Well, in this case, the components are not singular. Are just smooth rational curves intersecting transversely. But when you try to do this in higher dimensions, it's very likely that these components will have some singularities. So that's the motivation. And now let me give you the definition of what I mean with singular Fano, which from now on I will just call Fano. Okay, so when I say Fano, I will assume that I'm talking about singular Fano varieties, and when I'm talking about the smooth Fano varieties, I will add the adjective smooth. So a Fano variety, quotes, a Fano variety is a normal projective variety X with log terminal singularities and negative kx ample. So essentially this means that we have some curvature assumption, and then, which is a global assumption, and then some singularities assumption, which is a local assumption. Okay, so let me throw to you a couple more definitions. A log Fano pair, and then we will go with some examples. A log Fano pair is a pair x delta with negative kx delta ample. Again, well, when I say pair, I'm assuming normal, and with the second condition, you get projectivity, and x delta log terminal. Okay, so essentially it's like a pairs version of the previous definition, nothing new. And then we will say that a variety X is phenotype if x delta is log terminal and negative kx plus delta is nef and big, or big and nef, for some suitable delta. Delta which must be effective. So as you may remember from the last lecture, we would define log terminal type. So this word type always means that this condition is preserved up to some correction term that is this boundary divisor delta. For instance, you may have a variety which is not Q-Gorenstein. Then you try to find this delta to sort of approximate a log Fano pair. And you may wonder why we say phenotype if it just says nef and big. The reason is because if you write ample or you write nef and big here, essentially the same terms hold. So people usually work with this definition. So it's more broad, but it still works. That's the whole reason. Okay, so and let me just give one more definition, and then I will jump to some examples. So a pair, so I know this may be a little bit heavy for the first 10 minutes of the talk, but a pair x delta is quotes log Calabi-Yau if x delta is log canonical and kx plus delta is numerically trivial. Okay, so essentially these are sort of the log versions of the notions that I defined in the first talk, but also allowing suitable singularities. Okay, so let's see some examples, and then I want to add a 4 item here. Well, actually, I will erase this and then write the 4 item. So, for instance, and this is a nice exercise for the grad students. So, if you take P1 times P1, well, that's a smooth Fano variety, right? So, exercise. So, if you take P1 times P1, this is a smooth Fano. And if I blow up all the torus invariant points, all torus invariant points, and then you get x to P1 times P1, meaning that you blow up 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1. Then x is not Fano. However, x is phenotype. So essentially, the game is that you need to find the combination of the exceptionals and the four torus invariant lines in P1 times P1 that will make this condition be true, that you will have a log terminal pair and negative kx plus delta is nef and big. Okay, so actually, a remark after you complete this exercise, if you know some toric geometry, you can prove the following statement. Any projective toric variety, let's say projective normal toric variety, is phenotype. So it is not true that projective toric varieties are Fano, right? I mean, first, you may not have the Q-Gorenstein condition. But you can always find a torus invariant boundary such that this condition is satisfied. Okay, so this is just this problem. If you want to solve, if you want to give a proof of the remark, this is just a problem about convex geometry. You try to find a polytope, and you try to move the vertices around to make it reflexive, essentially. So let me write down the following theorem, which is due to Prokhorov and Shengjiang in different dates. It was finally proved in 2014. So essentially, Prokhorov proved this theorem up to some MMP tools, and then Shengjiang proved these MMP tools that allows you to finish the proof. So let X be a log terminal singularity. Then there exists a projective rational morphism. A projective rational morphism. Pi from Y to X with extracting a unique divisor E, extracting a unique normal, and then projective, because the morphism is projective, divisor E with pi of E going to the point. And, second condition is that X minus the point is isomorphic to Y minus E. And finally, E is Fano type. It's not necessarily Fano, but it's Fano type. So essentially, this means that if you want to study a log terminal singularity, you can perform a blow-up such that the effective exceptional, the exceptional divisor is a Fano type variety. And then once you have this kind of blow-up, what you can try to do is to do the degeneration to the normal cone. So a corollary of this theorem is that every log terminal singularity degenerates to the cone over a Fano type variety. So now we have the two processes. So I explained one in the first lecture that we can take. Oh no, it was the second lecture, that taking cones over Fano varieties give us log terminal singularities. Well, I did not explain the statement, but at least I stated. And now we have some sort of other direction, which says that if you have a log terminal singularity, then there is always a blow-up that extracts a Fano type variety over it, and then you can do a cone degeneration to the cone over that Fano type variety. So we have this process. So it would be beautiful if we could have some sort of bijection between Fano type varieties and log terminal singularities of one dimension more. But this is, of course, not, I mean, maybe not of course, but this is not true. So on one hand, you have Fano type varieties of dimension n. And let me mention, I did not write it, but you can write log terminal type here too. Okay, so you can add the word type if you wish. So let's keep this word all the time. So if you look at Fano type varieties of dimension n, you can use cones to construct log terminal singularities, log terminal type singularities, log terminal type singularities of dimension n plus 1. And then you can use these blow-ups that are called purely log terminal blow-ups. Let me not get into why are they called these, but purely log terminal blow-ups. And this is too many words. It's 5, right? And this is something we want to say fast, so we call them PLT blow-ups. And then you can use PLT blow-ups to study n plus log terminal type singularities of dimension 1 using Fano type varieties of dimension n, so PLT blow-ups. And then it will be beautiful, right, if this was like some sort of bijection that you go to one side and then you go to the other side and you recover your initial singularity. But this is very far from being a bijection, right? For instance, you can have the smooth point And then what would be a PLT blow-up is just blowing up the maximal ideal at the origin, if you want to study the smooth point. And here the exceptional divisor is the projective space of dimension n-1. But then you can do any toric blow-up, and the variety, sorry, not any toric block, you can do any blow-up of the ideal. For instance, you can take AN, and then you can blow up the ideal x1 to the alpha 1, L to the alpha L. Here you need to, yeah, no, that's fine. I mean, you need to put some conditions to make sure that the ideal is saturated, and then you will perform a blow-up that will extract a weighted projective space. So this is, let's call this I. Then you blow up I, and then the exceptional is some weighted projective space. I think it should have the same weights. Right, so this process is not unique. Over a log-terminal singularity, you could have a lot of PLT blow-ups that are extracting different phenotype varieties. And this process actually is also not unique, right? Because you can take the cone over negative kx, but you can also take the cone over multiples of it, and it will give you different singularities. So, okay, but that's life. We move on, and we still try to use these theorems to prove things, right? So what is the fourth reason of, or the fourth motivation of studying singular Fano varieties, or more generally phenotype varieties? So the fourth motivation is that it allows to, so you go back in your notes, and now you can add 4 to the first answer, the first question of this lecture. Singular Fano varieties, or more generally phenotype varieties, singular Fanos, allow us to understand log-terminal singularities. Okay, so here one needs to be more precise, of one dimension more. Okay, so here one needs to be more precise, you need to say phenotype, singular phenotype, and log-terminal type. But let's forget those words for a second. Okay, so let me tell you what we know about singular Fano varieties. And let me not, I don't want to spend a lot of time on this because, I mean, we know quite a lot, but classification-wise, at least, we know very little. Like, let's say that the cases, the classes of singular Fano varieties that we can completely classify are rather small classes yet, right? Maybe we'll do progress in the future. So let's see. So what we know, quotes classification-wise, right? So not qualitative results, but rather which cases we can classify completely up to isomorphism. Classification-wise. I'm pretty sure this word doesn't exist, but we will use it. Okay, so first, well, we have the smooth cases, the smooth Fano varieties that we can classify in dimension 2 and 3. Let me skip those because now we're talking about singular Fanos. So what we can do is, for instance, canonical Fano surfaces of Picard rank 1 are classified by Mianishi and Zhang in 88, are classified. Okay, so let me say that very likely I will get this number wrong. Maybe some grad student in the audience can. I think there are 28 families, and I think there are almost, these families contains the smooth ones as well, the 10 smooth families, and the other 18 singular families, they're almost all just one variety. They tend not to have deformations. There is just one family that has moduli. And they are mostly determined by their singularities. So if you look at the singularities, you usually can tell which isomorphism class of the surface you got. So this is Miyanishi and Zhang in 88. And I think that there are some classifications of canonical Fano surfaces in general, but I'm not totally sure if we have them up to isomorphism. Maybe there's a little caveat in that classification. There are some singularity types that we don't know if they have 2 or 3 different isomorphism classes. Okay, but let me not get into those details. So then you can ask about terminal Fano threefolds. Questions? Oh, canonical singularities, right? Right. Before we were talking about smooth Fano surface, now we're talking singular Fano surface, and this means that it has canonical singularities. Thanks for the question. So if you ask about terminal Fano threefolds, this is still open. I think we have several thousands, or at least 1,000 terminal Fano trifles. So not classified yet, but there is a lot of explicit work in this direction, and I think this class may be eventually classified in the next few years. I don't know, 10 years, who knows? But a lot of explicit work. And let me not mention names. I mean, I will have to write a huge list of names. So there is, there is Young, Corti. Okay, it's too long. So let's say a lot of birational geometers are working on this. And then let me write the name of Cheng Yang because it's the one that I mostly remember right now. And then you can ask me about the toric case, right? So we say that the smooth toric varieties can be classified by reflexive polytopes. And then there is a similar story for canonical toric Fanos and canonical toric Fano varieties. Canonical toric Fano varieties are classified up to some dimension. Up to, let me say dimension 6. The last time I checked was several months ago, so maybe now we have dimension 7. But let's say that we actually have the algorithm. It's sort of lack of computer power, what we don't have. Or maybe a smarter way to write the algorithm could help, right? So, here let me mention Benjamin Neal. There is also Alexander Kaprishik, a lot of people from mirror symmetry that are interested in these things. And something interesting is that I mentioned that we expect that the smooth toric Fanos grow like 10 to the n. These ones grow doubly exponentially with the dimension, at least with the data that we have. So they grow doubly exponentially. Doubly exponentially with the dimension. Okay? And as far as I know, these are like most of the classes of singular Fano varieties that we can completely classify. If you go up in the dimension, then you run into the same problem that smooth Fano varieties are not classified. And then good luck with the singular ones, right? So instead, we will start doing qualitative mathematics from now on. So meaning, let's try to describe the main characteristics of singular Fano varieties rather than try to write down all the equations explicitly because it's very unlikely that we will achieve that. So let's see. So now actually I will recall an invariant that I defined in the last 10 minutes of the last talk, which is the regularity of a pair. And we will start from here trying to do some qualitative study of singular Fano varieties. So, okay, so now let me write again that very ugly definition, but this time I will give examples. So hopefully we don't get lost. So let x delta be a log pair. And sorry, but I've been sort of missing this word many times. I use them as synonyms, log pairs and pairs. Depending of which papers you look, some authors use log pairs and authors use pairs. So the regularity of x delta was this huge maximum definition, is the maximum k, and here I will need a lot of space, such that there exists a log resolution y to x, let's call it pi, of the pair, not of x delta, such that if ky plus delta y is the pullback of kx plus delta, then we can find k distinct prime divisors S1 sk inside delta y equals 1. So this means, so let me write it here not to make the definition even longer. This means the components of delta y with coefficient 1. Components is the sum of the components of delta y with coefficient 1. And then we ask that the intersection of all of them, not the intersection 2 by 2, is non-empty. And we close the parentheses, and then we subtract 1. Okay, this is just, I will explain this in a second, why this minus 1. Okay, so that this definition makes, I mean, it's ugly, right? So let's compute some examples and try to digest what this really means. So let's just take some examples of surfaces, not to make our lives so complicated. So if you take, let's say, A2 with 2 lines, like 2 lines with coefficient 1. So this will be the pair. A2, L1 plus L2. Okay? So what is the regularity of this pair? Well, you see that there are, well, we don't need to take a log resolution, right? This pair is already log smooth, so we can start checking the regularity here. And we have 2 components that intersect non-trivially. So K will be 2 in the definition, so the regularity will be 1, right? The regularity of A2, L1 plus L2 is at least 1, right? Because I provided one example and we're taking a maximum. But you see that the fact that y delta y is log smooth, in a surface you cannot have more than 2 curves, log smooth divisor intersecting, right? You cannot have 3 curves through a point. That's not SNC, so it wouldn't be a log resolution. So this is precisely the regularity. So the regularity is always up to n minus 1. So note that the regularity of a pair, x delta, is at most n minus 1. So what about a more complicated example? So let's say A2, and then you write 5 over 6 times a cusp. Okay, so this one is more complicated. So this one is, of course, not SNC because, I mean, it's not log smooth because the cusp is singular at the origin. So I need to blow up. So I will blow up the cusp that I will just denote by C. And then I will have the exceptional divisor. And then when you blow up a cusp, you get, well, this is just the cusp, and it will be tangent to the exceptional. So what is the coefficient that I get on the exceptional when I take log pull back? So when I pull back the canonical of A, I will get coefficient -1. And then I will have to add 10 over 6 because it's the cusp with multiplicity, well, the cusp has multiplicity 2 at the origin. So I have to do -1 plus 10 over 6, which is 2/3, right? Let me check my notes. I did not bring this one. So, yeah, I think this, okay, this is so embarrassing. Please delete this part after the talk. So this is 2/3, right? Yes. Okay, and then this is still not log smooth, right? This is not a log resolution that we're asking the definition. We have to blow up one more time here. And then you will get this picture. So this is E. This is the second exceptional. And this is the strict transform of the cusp. And this is 2/3. And what is the coefficient of the last one? I think it's 1/2, right? Yes. Because it should be -1 plus 2/3 plus 5 over 6. And this should be 1/2. So this is the log pair. This is what I'm drawing here is delta y. And now I blow up a last time here to make it a log resolution. And what I get is 1 on the last exceptional, let's call it G. Here I have F, E, and the strict transfer of my cusp that I will just keep denoting by C. Sorry if this is a bit annoying for some of you. And I have 1/2, 2/3, 5, 6. Okay, and this is a log resolution. And you see that there is a unique divisor with coefficient 1. So in this maximum, I can take K at most 1. But then you can ask me, well, what if you keep blowing up? It's not hard to prove that if you keep blowing up forever, that's the only guy that you will see with coefficient 1, right? In any possible higher model. Okay. So we conclude that the regularity of this guy is equal to 0 because you can take K equal 1 and then you have to subtract here. And this is not hard to see that if you compute the regularity of A2, and then you subtract an epsilon from 5/6. And why? OK, so now the question is why I choose 5/6? Because it's precisely the number that makes this curve appear with coefficient 1. OK, you can check that this is what we call a log canonical threshold. It's the largest real number or rational number that you can write here, such that this is log canonical. So if you subtract epsilon from the cusp, you will get a regularity -1. So these are the only 3 possible cases. The regularity is always between -1 and n-1. OK? So essentially, the way that I explained this is that the regularity of a pair measures like sort of the complexity of the resolution. If you have high regularity, it means that in the log resolution, you have a lot of divisors intersecting together with coefficient 1. So it's sort of like a large complex in your space. Any questions about this? If the coefficients are wrong, I exercise for the grad students find the right ones. Sorry, can you say that again? Oh, because this guy has multiplicity 2 along the point, so when you pull it back, Harshon 3 to 10 or something like that, you get C plus 2E, so you get 2 times 5/6, right? Oh, this is the node, right? If you have just one component, so I mean, this is the node locally, right? Yes. So the regularity will be 1 if they both have coefficient 1. It will be 0 if just one of them has coefficient 1 and the other has less than 1, and it will be -1 if they both have coefficients less than 1. That's the trichotomy. OK, so I hope the concept of regularity was more clear now, because now we're doing it in asteroids, so meaning that we're using it heavily. So I will define 2 concepts, the corregularity of a singularity and the corregularity of a Fano variety, which essentially measures what is the worst combinatorial structure of a boundary that you can put on these objects. So let's see the first definition. So let x delta x be a log terminal singularity. The absolute regularity of the quotes, absolute regularity of x delta x is the following invariant: reg hat x delta x will be the maximum of all the regularities of pairs of the form x delta plus b at x with 2 conditions: x delta plus b LC and b larger or equal than 0. OK, this looks a little bit obnoxious, right? Wait. This looks a little bit obnoxious. I mean, it doesn't tell you much, but let me explain it in words. So you look at, let's set delta equals 0 for the time being. Essentially, you are looking at all the strictly log canonical structures that you can find through the singularity, and you're trying to maximize the regularity. OK? In that way, it sounds a little bit better. So if you take just the germ A2, the absolute regularity of A2 is 1, right? Because we test different boundaries that are log canonical, and the largest one that we got is 1. Actually, one can show that. So let me erase examples and write a remark that the absolute regularity of a toric singularity is always the dimension -1. So remark, and you just choose the toric boundary, the reduced toric boundary through the singularity. The quotes absolute regularity of a toric singularity equals 0. Oh, sorry. Dimension -1. Dimension of the singularity, of course. Okay, and now we will define the absolute co-regularity. Okay, so what is the of x delta at the point? So what is the motivation for this new invariant? And is that, for me at least, the invariance should be closer to 0 when they achieve the simplest structure, right? And so I am uneasy with an invariant that takes high value for toric variety, so I will just invert it to make the toric case to have value 0. So this will be, I will write correg delta x delta will be the dimension of x minus the absolute regularity minus 1. So now, essentially, by definition, the absolute co-regularity of any singularity, actually, you don't need it to be log terminal. So by definition, the absolute co-regularity of any log pair or log pair singularity belongs to the set 0 and dimension of x minus 1, and all toric singularities have absolute co-regularity 0. So now you can use this as some sort of measurement of how far are you from being toric. So if you have high co-regularity, if you have a high absolute co-regularity, then you have a short argument for non-being toric. So now I want to do the projective analog, right? So this talk is about singular Fano varieties, and I'm defining this for singularities. But the point is that there is a projective analog that I will write on the left side of the board. So now let's say definition, and here if I could copy paste in real life, I will just copy paste that and change log terminal with Fano and LC with Calavillao, and I will be done. You are totally right. So in that case, you get. Okay, I think that if I do that, then okay, that's why the negative one was. Yeah, sorry about this. I think if half of the times I get the negative one wrong in the definition. It should just be in one place. Okay, so definition. Let x delta be a phenotype, or okay, let's just work with x. Let x be a phenotype variety. I want 0. So, okay, no, so then I have to subtract -1. And what did I do wrong then? Okay, yeah, that not -1 is not here. Yeah. Sorry, I'm not extremely good with arithmetics. Yeah, this should be fine. Okay, so let x be a phenotype variety. Are there still complaints about there should be m possible values, right? Or m plus 1 possible values. Okay, that's fine. Okay, the quotes, absolute regularity of x delta. Oh, sorry. Now I'm writing the projective case of x is the absolute regularity of x, which is defined as the maximum of the regularity of x comma v, such that x comma v is Calavillao. Sorry, is log Calavillao. And then, analogously, the absolute co-regularity, so let me not write all the words, should be equal to the dimension of x minus the absolute regularity of x minus 1. And again, the absolute co-regularity of a Fano variety moves between 0 and the dimension. And for all torics, you get absolute co-regularity 0. So what is nice about this picture is that I told you that there is this, not bijection, but this way to go from Fano varieties and log terminal singularities, and try to use log terminal singularities to study Fano varieties and vice versa. And the nice thing is that these two procedures that I explained previously, which are the PLT blow-ups and the cones, respect this stratification, right? This stratifies all Fano varieties of dimension n in n+1 classes, and this stratifies all log terminal singularities of dimension n in n+1 classes, and this process respects the stratification. So you get that phenotype varieties of regularity, well, you can write co-regularity, regularity, it doesn't matter, of absolute regularity equal to R and dimension n, sorry, this is not very visible, correspond to log terminal type singularities of dimension n+1. Here I prefer to write co-regularity because otherwise I have to write a -1 again somewhere and I will again get confused. Of absolute co-regularity equal to C, and I already wrote the dimension. And then if you take cones, you go from this direction to this direction, and then you can take PLT blow-ups and you can go from this direction to this direction. So essentially it gives you a nice way to study these varieties inductively, but now it preserves this invariant that we define as the co-regularity. So one example of this principle is that toric singularities admit toric blow-ups, because the exceptional divisor of the toric blow-up is toric, so it has co-regularity 0, and toric singularities has co-regularity 0. And then if you have a toric variety, and then you take a cone over it, you get a toric singularity. So you see that in this instance, actually this process respects toric phenotypes and toric log terminal singularities. But it also respects this invariant called co-regularity. Yep. So why I'm talking about this? Because now I want to introduce, so we were talking about studying Fano varieties, singular Fano varieties qualitatively. So now let me introduce a theorem, and you should look at it and you should say, oh, but you already explained this, right? Well, the answer is no. I explained the local invariant of what I'm going to write now. And actually, this process is essentially the proof of what I will write now. Before writing the theorem, maybe I will give some examples. Yeah, let me take a few minutes to write some examples because I think this is important. So, examples. The co-regularity, the absolute co-regularity of an AN singularity is 0 because you can take the toric boundary. The absolute co-regularity of a DN singularity is still 0. It's essentially, I mean, you take the DN singularities admits 2-to-1 covers by AN singularities, and then you can take the quotient of the toric boundary, and that will give you a co-regularity 0 structure on the N. But if you look at the co-regularity, the absolute co-regularity of E6, E7, or E8, this is just equal to 1. And the reason is that this fork, this point at the fork, is the only divisors that you can make appear with coefficient 1 if you put any log canonical structure, any log canonical divisor curve, or any curve through the singularity that gives it a log canonical structure. So let's say the fork, I mean, from the perspective of Berkovic space, you look at this space of all the divisor evaluations, this fork is sort of at the bottom. So any curve will have larger multiplicity along the fork than all other divisors. So if we could embed the Berkovic space in something such that it respects multiplicity, we should draw it like a convex object. Well, sadly, it's infinite dimensional, so it gets harder to draw. And the fork point should be like a local minima for any linear function on this space. Okay, and this is the possible co-regularities of the ADE singularities. So now let me write a theorem that should look extremely similar to what I wrote on Tuesday. So the theorem is the following. And I will just leave this because essentially the proof is just, let's say, try to do this process, but keeping track of fundamental groups when you do it. So the idea of the proof is relatively simple. And of course, the proof itself is high machinery, but you have to do what you have to do. So theorem. And I think this was M21. So let X be a phenotype variety. Let X be a phenotype variety of dimension n and absolute regularity R. Then there is a local analytic embedding from D star to the R plus 1 into the smooth loci of X, such that the image of the induced homomorphism on fundamental groups so it will be set to the R plus 1 going to the fundamental group of the smooth loci of the phenotype variety is finite, abelian, it's finite. Well, let's not write abelian because it's rather obvious. It has rank at most R plus 1 because it has a surjection from F R plus 1. And of index, normal, that's what I'm missing. Otherwise, I can not talk about the, well, I can still talk about the index. And of index, at most, Kn. And this is precisely the same variable that I wrote on Tuesday. So essentially, this is the way that one proves the theorem that I wrote on Tuesday for log terminal singularities. You essentially, okay, so let me explain one more thing about this. This says that if you look at all the loops of the smooth loci of a Fano variety, then you can sort of retract them to, to a small analytic disk. And what I mean with a local analytic embedding, that means that it goes to a small neighborhood of a point in X. It's not like an analytic disk that will map crazily on all of X. I can send it arbitrarily close to a chosen point in X. So how this looks, it tells you that if you look at a singular phenotype variety, so here you have a phenotype variety. If you want to see examples of this, just take singular toric varieties, right? So if you have a toric variety, a projective toric variety, all whose torus invariant points are singular, then it's very likely that the smooth loci will have some interesting covers. Okay, and that will give you examples in which this R is equal to n, and you will have finite groups that are abelian and arbitrarily large. So if this is X, so how this looks, here you have the singular points of X. And the theorem tells you that if you want to study covers of the smooth loci, so covers ramified at least points, then there is some sort of analytic neighborhood here that I can choose arbitrarily close to some points. It may be singular, it may be not. So this is dr plus 1, such that it's not dr plus 1, it's d star r plus 1. So this is, okay, I'm very unhappy how this is equal to d star r plus 1, this thing here, such that essentially almost all the loops collapse to this neighborhood. So essentially this is saying that quotes the fundamental group of a Fano variety can be again controlled by not toric geometry, but something that looks like pretty much like analytically toric geometry. Okay, and the proof is essentially try to do local to global principles. So first you prove it for surface singularities, which is like a very easy computation. You use in the case of surface singularities of some regularity, you prove it for Fano surfaces with the same regularity. Then you use this with PLT blobs to prove it for log terminal threefold singularities with the same regularity, and then you keep going up. That's the whole idea of the proof. So what is an outcome of this? So a corollary of this statement is that Fano varieties with the smallest regularity, with regularity -1. So if you take r equals -1, then this is just, well, this is nothing. This is a point. So then what we're saying is that the order of the fundamental group of the smooth loci is bounded in terms of the dimension, right? It's a finite group of order most kn. So the corollary that you get is that Fano varieties with regularity -1 and dimension n have Fano varieties X have size of the fundamental group of the smooth loci bounded above by Kn. And this is something, this is something quite interesting because whenever you see some sort of finiteness in the topology of a class of objects, you start wondering something like, are these objects bounded or topologically bounded or something like this? And one more comment is that in recent work with, okay, so let me write as a remark this, that the expectation is that this Kn is something like a 2n factorial, or let's say similar to, or O 2n factorial. Right, so this is the expectation. And then we have work with Luis Esser and Lina G in which we prove some particular cases. So we look at symmetric actions on Fano varieties because, you know, if you have a symmetric action on a Fano variety, you can quotient by it, and now the symmetric group will appear as a homomorphic image of the fundamental group of the smooth loci of the quotient, and then you expect that appears in the co-kernel here, right? Because no abelian group can map non-trivially to a symmetric group. Well, only says 2, but essentially to understand this constant, it's very natural to look at symmetric actions on Fano varieties because you expect that the symmetric groups tends to be the largest finite groups acting on rationally connected varieties. And we get something very close to this for symmetric actions. Oh yes, this Kn is the same as the Kn that I wrote on Tuesday. So it's a constant that only depends. Yes. So okay, so if I want to be more complete, one should write here, fix n a positive integer, then there exists Kn satisfying the following. There exists Kn satisfying this. And then as an observation, this Kn turns out to be the same Kn as in the theorem on Tuesday. Okay, so then, what is the name of this? Actually, these Fano varieties have a name, and that name is exceptional Fano varieties. So, definition: an exceptional Fano variety is a Fano variety X for which the co-regularity, the absolute co-regularity is equal to its dimension, which is the same as saying that the regularity is equal to -1. So if there is people from the like a more birational flavor inclined, I will say that This should be if and only if the alpha invariant is larger than 1. So these are called exceptional Fano varieties. And so this class is very special, right? So their fundamental groups are sort of controlled. So if you remember from the first lecture on Monday, we discussed this Kollár-Millau-Okamori theorem that says that the class of n-dimensional smooth Fano varieties is a bounded class, meaning that you can parameterize all of them with a projective morphism between finite type schemes. Then you may wonder the same, right? Is it true that all Fano varieties of the same dimension, meaning log-terminal Fano varieties, are bounded? So let me explain why this is not the case. Let me raise this one. So we're still in the line of trying to understand qualitatively singular Fano varieties. So now we understand pretty well their fundamental groups, I will say. There is still a few open questions in this direction about which fundamental groups appear, which fundamental groups do not appear, but we have good tools to tackle those questions. So now let's change topic and let's discuss about boundedness of Fano varieties. So you can ask the very naive questions. Are all Fano varieties of the same dimension bounded? So are all the Fano varieties of the same dimension bounded? So the answer is sadly no. And I can give you a pretty easy example. So let me not give a full proof of this, but at least the argument. You can take weighted projective spaces. For instance, something very simple, P11n, where n goes to infinite. This gives you a finite sequence of singular Fano surfaces with quotient singularity, hence log-terminal singularity. So these are Fano varieties, Fano surfaces, and one can check that they have singular points, and these singular points, which are cones over smooth rational curves of degree n, these singular points in these Fano surfaces have larger and larger embedding dimension when n grows. So the embedding dimension of the weighted projective space goes to infinite in particular. And if you have a bounded family, you can embed the whole family in with a projective morphism. You can embed all the fibers in the same projective space. So it is impossible that all these varieties appear in a bounded family. So this gives the answer. Okay? So, however, there was a breakthrough in 2016 by Kocher-Birkar who proved that this is true if you control two invariants, if you control the dimension and the singularities of the Fano varieties. And what do I mean with controlling the singularities? So let me write one more definition. A Fano variety X is epsilon log terminal if all its log discrepancies are larger than epsilon, right? So we define log terminality as being all the log discrepancies are positive, right? So now we're asking them that they're away from 0 in some sense, okay? So 0 log terminal is just log terminal. Is equivalent to log terminal. And 1 log terminal is the same as some grad student that is paying attention. Some postdoc that is paying attention. To terminal, right? Who was that? Was that Jenny? Okay, it's just terminal. Okay, so it's like a measurement. It's like a measurement between terminal and log terminal with a continuous variable. So the theorem that Birkar proved is that. Oh, before the theorem. So you can see that these varieties are, so these Fano varieties, let's call them xn. So if xn is p11n, then, sorry about this awkward use of the word, xn is, let's say, 1 over n LC, sorry, LT, log terminal, but not 2 over n log terminal. So essentially, this epsilon that measures the singularities is going to 0 in this sequence of examples. And this divisor, the divisor that computes, oh wait, I say it wrong, right? Let's say 2.5 here, this should be larger. Okay, 2.5, sorry. It's 2.5 over n log terminal, but not 2 n log terminal. And the divisor that computes the log discrepancy equal to 2n is precisely the blow up at the vertex of the weighted projective space that gives you the Hirzebruch surface, sigma n. Okay, that exceptional divisor is the divisor with log discrepancy equal to 2n, which make it not 2 over n log terminal. Okay, so what Birkar proved in 2016, well, he proved a lot of things, but let me give you 2 highlights of this, is that, well, first, if you fix n a positive integer, and epsilon positive, then the class of n-dimensional epsilon log terminal Fano varieties is bounded. And then, so essentially this example is the optimal example to disprove the statement, right? Because it's precisely where the epsilons are going to 0. And if you like toric geometry, controlling this epsilon, okay, do I want to say this? So controlling this epsilon in toric geometry correspond to controlling some angles, corresponds to controlling angles in the polytope away from 0. So meaning that, okay, so let me not be precise in this statement because it actually requires much more machinery to make precise, but a toric variety is epsilon log terminal if the angles that you see in the polytope are larger than some functions of epsilon. So essentially what this term tells you in the world of toric geometry is that if you look at certain possibly singular reflexive polytopes, if you don't allow very small angles, then you have only finally many polytopes. This is the corresponding statement. And this statement for toric varieties was actually proved by Borisov, Alexeyev and Borisov. So this was called the VAV conjecture for a long time because they proved the toric case. And then Birkar used some theory called the theory of complements to prove the general case. And the last part of this talk today will be a brief introduction to the theory of complements, and I will share with you some recent developments by Figueroa, Filippazzi, Peng, and the speaker. Yeah. So the other theorem that he proved in this paper, which actually predates this one, I mean, not predates, but is used for the one above, is that if you fix n a positive integer, then the class of n-dimensional exceptional Fano varieties, so the ones of corregularity equal to the dimension, or with positive alpha invariant Fano varieties, is bounded. Let me just make a comment which is false, but it's a little bit how it works. For instance, if you have surfaces with E-type singularities, Fano surfaces with E-type singularities, they tend to be exceptional. Okay, this is not true. One needs to add a little hypothesis, but in general, in higher dimensions, Fano varieties with exceptional singularities tend to be exceptional Fano varieties. I can give a more precise statement if you. Exceptional means that the alpha invariant is positive, or you cannot create any log canonical center with complements. Or using the language that I introduced, the co-regularity is equal to its dimension. Okay, so the main tool that Birkar used to prove this theorem is called boundedness of complements. So let me define complements and write the third theorem by Birkar. And then I will tell you what has been the development since then in the last few years. So now we're going to start with any variety. So definition, let X be a variety. Be a normal projective variety. A Q complement is a divisor B, which is effective, and Q equivalent to negative Kx, for which the pair XB is log Calabi-Yau. So essentially, a Q complement is nothing else than a Q Calabi-Yau structure on your variety. Sorry, a log Calabi-Yau structure on your variety. So even in a fixed Fano variety, you can put infinitely many of these. So for instance, in P2, a Q complement will be 3 lines with coefficient 1 because it's log canonical. But you can also take a conic and a line. You can also take a smooth elliptic curve, or you can take a nodal cubic. Okay, that's a bit boring. Let's do something else. Or you can take 1 line and 4 general lines with coefficient 1/2. Well, those do not look very general. But this is another Q complement, right? If you take all the lines general, one of them with coefficient 1 and all the other with coefficient 1/2, you get something that's log Calabi-Yau. And in this case, 2V is equivalent to negative 2Kx, so V is Q equivalent to negative Kx. So a complement is nothing else than a log Calabi-Yau structure. And we say that a Q complement is this is not what I'm defining. A Q complement B is said to be a N complement, if N times Kx plus B is linearly trivial or linearly equivalent to 0. So an N complement is nothing else than a nice element, a nice boundary divisor with log canonical singularities in the linear system negative N Kx. So if you want to prove these boundedness statements, you need to produce a lot of anti-canonical sections, because the idea of the proof of these two theorems is that you want to embed all these Fano varieties in the same projective space. Hence, you need to produce a lot of sections in some uniform multiple of negative Kx. So you need at least one complement, right? So the first statement that you need to prove is some sort of boundedness of complements, that you can control the N in which you can find this structure. So if we look at these examples, this is a 1 complement. 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 And this is a 2 complement, right? Because this divisor is not equivalent to negative Kx. It's not even Wahl. It has a lot of fractional coefficients. But twice the divisor is equivalent to negative 2 Kx. And then we can also keep track of the corregularity. This one has corregularity 0. This one has corregularity 0 because it has these maximal intersection points. This one has corregularity 1. And this one has corregularity 1. So it's just to give you different flavors of these things. So the main tool that Birkar used to prove these two breakthroughs is the following theorem that is nowadays known as boundedness of complements in algebraic variety, in algebraic geometry. And it says the following. Actually, you don't need to erase this one. The statement is very close. I mean, it's very short. And it's the same paper. Actually not. So this is singularities of linear systems and unboundedness of Fano varieties. Okay, let me not write the whole title, but in case you're interested. And these two theorems are in a paper called Antipluricanonical Linear Systems on Fano varieties, or I don't remember if it says on Fano varieties on the title or not. Okay, so as an advice, if you're a grad student, okay, if you like hardcore things, read these papers. If not, there is a lot of good surveys. Like there is some surveys by Virkar himself, but there are others by Janning Xu. So if you like very long, very technical proofs, then go and read the whole paper and enjoy yourself. But there are some surveys by Janning Xu and some other people which explains more or less the ideas of these proofs without much technology. Actually, even understanding even understanding the proof for surfaces very well is something that already enlightens you a lot. So this is called theorem by Virkar, and this is known as boundedness of complements, and says the following: let X be now let me get my logic straight. So fix n a positive integer, then there exists n of n satisfying the following. For any n-dimensional Fano variety, let me just write it as this. Any n-dimensional Fano variety admits a n complement, n of n complements, where this means that it's a function on n, it doesn't depend on anything else. So essentially what Virkar told you is that if you look at all Fano varieties of the same dimension, there is a uniform multiple of the anti-canonical that is non-empty. And moreover, that multiple of the anti-canonical has some element with nice singularities. It's not just non-empty, but has some element with nice singularities. And this was the real breakthrough. I'm not saying that the other two follows immediately, but once he proved this one, everyone knew that he was going to do BAV very soon, and that was correct. 3 months after this paper, he posted the one on the top. So let me tell you, once we have this qualitative statement, then you can ask yourself, well, can we do it quantitative? So can we actually understand n of n in terms of n, right? And the answer, well, I'm not claiming that the answer is no, but the answer is not nice. So in 2020, Totaro proved the following theorem. So, theorem. Totaro, I think it was 2020, maybe 22. Okay, I think it's 22. So, n of n, let me not write the whole statement, but n of n grows at least doubly exponentially. Actually, I just remember. So if you go to the webpage of Tsinghua University, we had a Zoom seminar with Virkar and many of his co-authors where we gave a lot of lectures on the proof of these two theorems. And the idea is that, they're all recorded, and let's say that some of them were very heavy, but at least in all the talks, we tried very hard to give a lot of sketches before getting to the darker details. So Totaro proved that n of n grows double exponentially. So he gives essentially to prove this, you just need to produce examples, right? In which the n for that variety, the n of n for that variety is very large. So an example that he gives is that there is a Fano fourfold, X with negative, the linear system negative mkx empty for all m less than or equal than 4,677,233. So what this means, what is the interpretation of this statement? If you want to do an anti-canonical embedding of this Fano fourfold, well, you need to multiply, you need to find a very large multiple of this guy, and you will end up doing an embedding into a 10 million dimensional space with degree 80 millions or something like this, right? So, right, that's yeah, you did the right movement for this. So, seems hopeless, right? And then when something seems hopeless, we need to try to make hope appear again. And one more comment is that it's not part of the statement, but this X is exceptional. So now let's look again at the table of corregularity. But before going to the table of corregularity, let me make the remark that all toric varieties admits one complement of corregularity 0. All toric varieties. And this statement is totally independent. All toric varieties admit one complement of absolute corregularity, or no, the complement has corregularity 0, not absolute corregularity 0. So this statement is rather easy to prove. You just take the reduced toric boundary. The reduced toric boundary is an anti-canonical divisor. It's actually equivalent to negative kx, not q equivalent. So the toric boundary, the reduced toric boundary is a one complement. And then just by taking a log resolution of your toric variety, you see that there is n divisors intersecting, n divisors with coefficient 1 intersecting at a point, so the corregularity is 0. Okay? So if X is a Fano variety, right, we know that the absolute corregularity, Fano variety of dimension n, we know that its absolute corregularity is between 0 and n, right? And these ones are called exceptionals. And by Birkar boundedness of exceptional Fano varieties, these are bounded. So meaning that these examples could be very ugly, as Totaro showed us, but there are only finally many families of these. So if you want to do, let's say, a study of Fano varieties of a certain dimension, exceptional plus bounded. If you throw away all of these, you are not throwing away a lot, right? And here you have all the torics. So all torics belong here. All torics are here. Right? So these are finally many families, and all toric varieties are countably many. Right? They correspond to all possible polytopes. And as you see with weighted predictive space, we have infinitely many. Right? So if we throw away these guys, I'm not losing much. Right? I'm throwing finally many from countably many. So fair enough, right? So what we try to do is, okay, so in this case we have more hope to prove a better statement than what Birkar proved. So this is what we did, and essentially the proof used something introduced by Kawamata. It's called the X method, which means that you try to lift sections from log canonical centers. So I'm not going to explain the details of the proof. I'm just trying to give the overview of the landscape of what we know. So, and actually this proof, and actually this invariant corregularity started in a learning seminar that I ran between 2020 and 2022 on the minimal model program. So someone was giving a talk, and after the talk I asked a question, and then after a few months we realized that we could prove something maybe not better than this, but a version that seems worth stating. So the theorem is the following. Let me write up here. So this is work together with Fernando Figueroa, Stefano Filippazzi, that is, well, Fernando, right now he's nothing. He finished grad school and haven't started the postdoc yet. but he will be a postdoc at Northwestern in a few months. Stefano is a postdoc in EPFL. Jung Yao Peng is, no, I think he should go at the end. Well, Jung Yao Peng is a grad student at Princeton, and myself. So this was 22. So we proved that a Fano variety, and note that now I'm not going to fix the dimension. I will just say a Fano variety of absolute corregularity 0 admits either a 1 complement or a 2 complement of corregularity 0. So essentially, also in particular, negative 2kx is non-empty. So for these varieties, you expect that they will be more manageable. These Fano varieties should look more like toric varieties. They should have a boundary structure that looks quite close to a toric boundary. Of absolute corregularity, 0. I'm pretty sure I said it, but I didn't write it. Of absolute corregularity 0 admits either. Thank you. So this is a generalization of the fact that the toric boundary exists for toric varieties, right? So these corregularity zeros have a nice anti-V canonical, I don't know how to say it, a nice element in negative 2kx, which resembles the toric boundary. So let. It's 4. The exceptionals are the ones that take corregularity equal to the dimension. So this example has corregularity 4, and actually one can show that the sequence that he takes is a sequence of n-dimensional, where n grows, n-dimensional exceptional Fano varieties, so the corregularity is always maximal. So essentially, the whole idea of this proof is try to do induction on the dimension, but always avoiding the exceptional case. Yeah. So. That's a very good question. I think I maybe can. But if I can control the multiple that will make this system birational for corregularity 0, I think that's, not from the top of my head, but it's something I would really wish to do. So, which is very reasonable, right? But because all toric varieties have corregularity 0, they're all they're all very different up to isomorphism, but they all map birationally to the Brierley space, right? Yeah. So the answer is that maybe with some control in the singularities. I did try to prove this after this theorem, but I stopped doing it, and now I'm wondering why did I stop trying to do that? Okay, so what is my proposal? My proposal is that we should forget about Fano varieties, well, maybe not forget. But first, we should try to focus on corregularity 0. Right? Because if we don't have an understanding of corregularity 0 Fanos, the rest seems pretty, well, this seems very hopeless, right? But I have the hope that maybe the corregularity 0 Fano varieties, we could get a much better chance to do classification and do something much closer to classification. So, let me explain one last thing in the 6 minutes that I have. So if you look at n-dimensional Fano varieties, so you have this class here. N-dimensional Fano varieties. So this is not a set. Well, if you fix the field, then it can become a set. But you can move the field around, and this is just a class of objects. And inside this, you have the n-dimensional rational Fano varieties. N-dimensional rational Fano varieties. And here you have n-dimensional corregularity 0 Fano varieties. And both classes, of course, contain toric Fano varieties. n-dimensional toric. Here I'm not controlling the singularities. I'm just saying log terminal. So n-dimensional toric Fano varieties. So to finish this lecture, let me explain that neither of these contains each other. There are rational Fano varieties that are not corregularity 0, and there are corregularity 0 Fano varieties that are not rational. And I will finish with this, and then I will explain you what is the aim for tomorrow. So one example is actually, so I posted a paper on arXiv, and then someone told me that I did some counting wrong, that the theorem was the opposite. I fixed it afterwards. So what is the point? So let's say, so example. So let's say that X is a blow up at 8 points of P2. So I'm wondering if this guy has a corregularity 0 boundary. So let me at least argue for you that it has no. So my claim is that for some examples of X, meaning for some choice of the general points, there is no one complement, so no anti-canonical cycle. There is no one complement of corregularity equal to 0. So this is what I will argue. So what I will argue is that for some examples of X, there is no anti-canonical nodal divisor, so nodal curve. This is the translation of what I'm saying. So in this case, this is equal to no anti-canonical nodal cycle. Okay? And this doesn't disprove that X has corregularity 0, but because due to the theorem, you have to check one complements and also two complements. But let me say that the other case is pretty similar to what I will do. So what you do is, well, you take X and then you blow up the base loci of negative Kx. So you blow up. So this is pi. This is the blow up at Q of X, where Q is the base loci of negative Kx, and we know that this has an elliptic fibration down to P1. And this elliptic fibration, the isomorphism class of this elliptic fibration, depends on the Weierstrass polynomial on X in a weighted projective space. And for suitable choices of the Weierstrass polynomials, there is no nodal fibers. All the fiber will be either smooth or cusps. So that will tell you that for those examples, there is no anti-canonical nodal curve. So this is the proof. Okay, then one needs to prove that there is no two complements of corregularity 0. That's a little bit harder. One needs to analyze this elliptic fibration a bit more. But there is no containment of this set inside this set. Actually, the other direction, the fact that n-dimensional rational Fano varieties do not contain. Oh, wait. Did I say this wrong? Okay, I may have said it wrong, but sorry, it's been almost 90 minutes. So the second example was actually due to Kalogiros. So Kalogiros constructed, so I think this was around 2010. Sorry, I'm not very good with dates, but this is a theorem due to Kalogiros. In, I think, around 2010, that there exists a terminal Fano threefold, which is birational superrigid. So essentially, birational superrigid means that it has no more, any other birational model that is again a Fano variety of Picard rank 1 is isomorphic to the initial one. So let me just say that birational superrigid means the opposite to what rational means. Okay? So very far from rational. Superrigid that has corregularity 0. Okay, so let me just write it in nowadays terminology. What she proves is that there is some anti-canonical structure whose dual complex is a sphere. I will explain this wording tomorrow, but in the language that I introduced today, one can say that has absolute corregularity equal to 0. So in other words, absolute corregularity 0 is not containing rationals. As the previous example shows, the rational ones are not contained in the corregularity 0 ones. Okay, so my proposal is that although I say that this is hopeless to classify, and this may be, well, maybe not too easy, but totally combinatorial to classify, that's my timer, then maybe this is the right class to do classification of Fano varieties. I will stop here.